Okay, so this is that same problem I did during the live lecture. I'm just going through it again, make it a little nice and neat. So we've got this charge distribution here, a negative charge here and a positive charge here. We want to calculate the electric field at the origin from all this charge. And we made the argument in the live lecture that say we got some little bit of charge here. Remember, the electric field points toward negative charge and away from positive charge. So a little bit here would create a field that goes up. At this corresponding part, there'd be an electric field that would point down. The y components there would cancel out. So my total y electric field is 0. So the electric field is only going to be in the x direction. Remember, we're going to do an integral here, and we can only integrate component-wise. So I need to write, my goal is to write e in the x direction, because that's all that lives, as an integral. So I split up. Well, first, let's note that just by symmetry, whatever we get from this negative charge here, we're going to get the same contribution from the positive charge. Again, look at the other video to see that. So I'm only going to integrate from 0 to pi over 2 here for my angle theta. And whatever I get, I'll double it at the end. So I break up this arc into this little chunk here. Call this a little delta S. Now I know from experience from doing this problem, it's easier to integrate over theta, so I'm going to convert delta S into A delta theta. Remember, arc length, S equals R theta. Well, R here, our radius, we called A. So my little delta S has length, A delta theta, whatever that change in angle would be. Now, in all of these Coulomb's law problems, we always need to find delta Q. That's the key. And delta Q is always your charge density times your length. Charge density, lambda, is charge per unit length. Delta S was our length. So our charge density is the amount of charge here to here. We're only dealing with the negative Q part. Divided by the length. The length of this arc is a quarter of a circle. An entire circle would be 2 pi a, so a quarter of that is pi a over 2. So my charge density, coulombs per meter, is negative 2 pi, or negative 2q over pi a. So then delta Q is always lambda, delta length, whatever my measure of length is, but we just said delta S is A d theta, delta theta. So we get this quantity here. 2q over pi, the a's cancel, delta theta. Okay, now we look at our E vector. Remember, E in magnitude, this is Coulomb's law, is kq over distance squared. So E points up towards my little delta Q there. What I care about is the x component of that. Well, Ex will be magnitude of E cosine of theta. So here's magnitude of E. Notice I'm dealing with a magnitude here. I already know this is going to point in the positive x direction because we're attracted to negative charges. So I don't need to worry about that negative ever again. So magnitude of E is k amount of charge over distance squared. So I just threw in delta Q that we got right here in the positive version of it, right here. Then Ex will be that times cosine of theta. Now that's only the contribution from this little tiny bit of charge here. We need to add all those up. So if we were being very formal in a calculus class, we would have split this into n equal partitions. And this would just be the ith one, and we would have a sum from 1 to n. So we're kind of glossing over that. This is just one contribution. EX total then is the sum, approximately the sum from I equals 1 to n of all those individual contributions. We take the limit as delta S goes to 0, or in this case delta theta goes to 0. That sum becomes an integral. That d theta, or delta theta, becomes a d theta. And we put in our limits. The smallest angle for which this makes sense is 0. The largest is 90 degrees, pi over 2. So we get this integral that says 2kq cosine theta over pi a squared. All of this is a constant, so that can come out. 2kq over pi a squared comes out, and I'm integrating cosine from 0 to pi over 2. Antiderivative cosine is positive sine. So we evaluate sine from 0 to pi over 2. Sine of 0 is 0. Sine of pi over 2 is 1. So we just get 2kq over pi a squared. Now remember, that was only from this half. We need to double that to include this other half. So doubling that, we get 4kq over pi a squared. But remember, k is 1 over 4 pi epsilon naught. So we could, if we wanted to, throw in this other version of k and write everything in terms of epsilon naught. And we get q over pi squared a squared epsilon naught. That is the electric field at one single point, only at this point from this distribution of charge, and that point's in the x direction. So if we were going to write this as a vector, then this would be, there's the x component, and by a symmetry argument we figured out our y component is 0. An interesting problem is do this same thing using finding y here instead, this component, but then you got to actually do each part. You got to do the first part and the second part, noting that the first part all points up, the second part from over here, those all pointed down. The positive you get from the negative side, the positive y's, and the negative you get from over here, all these negative components, you'll get exactly the same number, but a positive and a negative, those cancel out. EY equals 0.